Perfect. All right. Good afternoon, everyone. I guess I'll kick off the student paper competition here. Today I'll be presenting on a decoupled model for the mean RCS of an object below a randomly rough surface, so sub-target detection. I'd like to thank my co-authors for this presentation, Dr. Joel Johnson and Dr. Robert Burkholder, and we are all at The Ohio State University. So the main application for subsurface detection has to do with landmines detection. There are over 100 million landmines placed throughout the world, 100 million more stockpiled, ready to go into the ground. And the removal process for these landmines is extremely difficult. There are two aspects of it. That is the actual detection of the landmine and the actual removal. Today we're going to be discussing the detection process. Landmines disproportionately affect civilians, thousands every year, especially children, so it's a very important problem. So there are many methods for detecting landmines. One of the more common ones is just a standard metal detector. However, not all landmines are made out of metal or conducting in any way. Sometimes they're like soccer balls. It's crazy stuff like that. So, that's not going to work in that scenario. Thermal imaging can be used. However, if your target is below the surface to any extent, thermal imaging degrades in accuracy. The one that we'll be talking about is ground penetrating radar, using like electromagnetic pulse actually transmit into the ground and try to get reflections from our landmine, in which is capable of detecting plastic landmines. One of the many issues surrounding detection has to do with the clutter caused by the rough surface, the rough soil surface. There are two ways that clutter enters your measurement. The first of which is direct backscattering from your rough ground surface. The second is actually the distortion that the rough surface is going to have on your subsurface target image. Generally, you're never going to actually know the exact conditions, the exact profile of your surface. So we're going to have to describe it stochastically. And since our surface is stochastic, the electromagnetic scattering is also going to have to be described stochastically. The way we're going to do that is using an ensemble average where we vary our surface profile and back out our surface statistics from there. So we're going to take the case of a very simple numerical problem of a dielectric cube about low dielectric. So it's plastic and very low resolution compared to our soil surface, which is also considered lossy. The target is going to be buried 1 inch down, and it's approximately in the S band. It's going to be around a wavelength. The surface itself we're going to be described as a Gaussian random process using a Gaussian spatial correlation function. Just keep it simple. The two parameters that are going to describe our surface stochastically is h, which is our RMS surface height, which describes the actual roughness of our surface, and L, our correlation length, which describes the relative smoothness of our surface. So again, our surface profile is unknown. So one way that you can solve this problem is to solve for a different set of ensemble averages. So for different surface realizations, we can see that the red dots correspond to the actual scattered waves for a specific surface profile, while the red line corresponds to the actual mean measurement, the mean RCS. Also keep in mind that blue curve up there is our actual surface average, which is in most cases going to dominate this problem, although this can be resolved using signal processing techniques. However, all in all, the Monte Carlo simulation of solving for meshing an entire surface and solving for it multiple times is extremely inefficient and needs to be improved. So I would like to take this time to note that we are not proposing a signal processing actual method like a hypothesis to actually detect the object. What we're doing here is actually formulating an efficient method to describe the statistical physical scattering of a subsurface target that can be used then to help in the development of signal processing methods and perhaps an AI training set data. So in order to get rid of surface meshing, we're going to want to solve for it analytically. Thankfully, there's been a lot of research done in this field. So just get a little notation out of the way so you don't get lost in the equations. We'll be tracing these, these plane waves are described using these k vectors here. The subscripts of 0 and 1 describe above or below the surface, and the positive and negatives correspond to positive and downward going waves in the z direction. So we're going to use these first order small slope approximation in terms of a plane wave expansion method. to describe the transmitted waves from a surface, although incident plane wave is going to have both scattered and transmitted waves, but since our target is below the surface, we're concerned about the transmitted waves. And an illuminating plane wave will set off a set of transmitted plane waves underneath the surface described using this F-kernel function, which is a combination of this SSA1 kernel function, which contains our polarization dependencies for this problem. And then what's more important is this diffraction integral, this IQ integral, which contains our random first surface profile, f of x of y. So this is our random variable in our problem, and solving for the statistics of this problem boils down to solving for the various moments of this IQ integral. So when you take the ensemble average of surface transmission, it can be broken up into two forms commonly. The first is coherent field, which is you're averaging with phase, and your incoherent power, which you're averaging the actual magnitude power of the transmitted waves. So generally, your coherent field is going to decrease due to this exponential factor seen in the blue equation, where h, again, is our RMS surface height. So as our surface roughness corresponds to our EM wavelength, our coherent field is going to rapidly attenuate. You can see that corresponding to that blue line right here in that, that refracted direction as you expect for a flat surface case. So it kind of has like this effective transmission coefficient. However, when our surface roughness increases, that coherent power doesn't just go away, it's just scattered in other directions, right? And that's what's caught in this incoherent power, right? Which exists in all these directions, not just in the refracted direction, and will increase with RMS surface height. The way in which this incoherent power is actually scattered or transmitted is due to this T2 integral function, which can be solved numerically. And you can see right here, as we increase our RMS surface height of our surface, or like increase our frequency, right? Our coherent transmission is going to rapidly attenuate, and then this heat map up here is our incoherent transmission, right? It's scattering all these different directions, almost in like a lobe sort of pattern. This is an ensemble average, so this is on average what your surface is going to do. So now here's our formulation. This is our proposed formulation of the total field for a target below a rough surface. Right now, we're ignoring the backscattered direction of our surface, although it is always there, right? So we're more concerned about, what is the target contribution of your field. Note that this method's also been applied for targets above a rough surface, so you can do below or above. So the way that this method works right here is we have this F-kernel function, which we were describing before, which describes our surface scattering matrix, and then you have this S-kernel function, which describes your object scattering matrix. So the way this formulation was derived is that you have this incident plane wave illuminating our surface, and you have a set of transmitted plane waves downward going towards your target. That set of incident plane waves will then result in another set of incident scattered waves in your target, which is what this S matrix is describing. Finally, those scattered waves are going to be transmitted into your backwards going direction, which is described using this F-kernel function. And then all of these plane wave interactions are going to be summed up in the K-space integral using this plane wave expansion method. So far, we've gotten rid of the actual meshing of our surface, right? We no longer have to mesh our really large electrical surface. But now we have yet to take an ensemble average of it, but which we can because we know the various moments of our F-kernel function, correct? So once again, we can split it up in terms of coherent and incoherent power, which again, simply just as the case for just the surface, our coherent power can be described as it would for a flat surface, just with an effective transmission coefficient, which attenuates with RMS surface height, right? So in this figure up above, we can see we have these, just a set of plane waves and a set of scattering plane waves from our object. That's all we have to account for. The incoherent part is not as simple as you would expect, because we're trying to find all these different scattering directions, not just one. It can also be broken up into two terms. First term has to do with will attenuate with RMS surface height. The second won't. The intricacies of these equations are not necessarily important for this talk, but what I want you to grasp here is that these K-space integrations are integrating over our target scattering matrix for all of these different plane wave interactions weighted by our T2 integral that we were discussing earlier for the stochastic nature of our surface transmission. So we're capturing all this physics that's happening underneath our surface and all these different scattering directions within these integrations. So now we can kind of play with our problem that we described earlier for dielectric cube. And the first variable we're going to play with is the RMS surface height. We're at 4 gigahertz here. So we're not nowhere near like a wavelength and RMS height, but still you can kind of see the behaviors of increasing the RMS surface height of our surface, right? So this blue line corresponds to our coherent part, which attenuates very rapidly with RMS height, and the incoherent part is increasing with RMS height and taking this place. The total mean scattered power really doesn't change a terrible amount, but what this really means for imaging is that incoherent power, right, describes like distortion. So for the larger RMS surface height you have a lot more distortion for your subsurface target image. And these simple formulations are capturing all this physics and all these interactions. So we also wanted to validate our method because we're assuming only one scattering instance with our target. We're not accounting for multiple scattering between our surface and our target. We wanted to compare it with a full wave method, which we did here. We're using a discrete dipole method, which is fast method, moment method. This required what we were talking about earlier, full meshing of our surface, which accounted for like 276,000 unknowns. And you had to do this 40 times, and you can really see the computation time difference between the two methods that we're discussing here. The DDM for 40 realizations required 6 to 14 hours per frequency to compute, while the iterative decouple method required 3 seconds. So massive leap in efficiency. And you can see in the plots over here that we're getting really good agreement. We broke it up in the coherent RCS in the top and then incoherent RCS in the bottom graphs. And we're comparing it for 3.58 millimeter and 1 centimeter RMS surface heights. We're really capturing a small roughness case and a moderate roughness case in this plot here. So now we can also play with other variables in this problem using the same two RMS surface heights that we were describing before with 3.85 millimeters and 1 centimeter, where the red in this case is incoherent power and the blue is coherent power. The differing, the dashes and the lines correspond to different RMS surface height here. So now we can, there's so many variables in this problem that you need to account for. So one of them we're taking account is the depth of our object, right? This is a lossy surface, so we expect, some sort of attenuation as our target gets deeper. And you can see that's being described perfectly with our formulation. We have this logarithmically linear attenuation with, as our depth of our target is increased. Similarly, we can increase the loss of our surface using, volumetric soil moisture, right? And it's very interesting in this case that our coherent RCS is actually much more affected by soil moisture than our incoherent RCS. So it's kind of an interesting thing that you wouldn't really think that would happen, that really shows up in our method. So in conclusion, the iterative decouple method models for the average RCS of a target below a randomly rough surface, up to first order scattering with our target, and it significantly increases our efficiency for solving problems of this nature, particularly by removing the need for surface meshing, right, really these large electrical surfaces, as well as removing the need for solving for many different surface realizations to get the statistics of our problem. And hopefully in the end, this will assist in the detection of landmines and therefore save lives. So for future work especially, we'd want to get into more of the time domain range profile instances of this problem, as well as the actual imaging of these subsurface targets and how the statistics are arranged in those problems. I'd like to thank the Air Force Research Laboratory for the funding of this research, and just know this is not their official stance and all that. And these are the references I used in the talk here. And are there any questions? Thank you.
The trade-off, you talked about S-band radar. Can you describe the trade-offs between going to L-band or X-band, for instance?
Well, yes, that's a good question. So it's kind of this give and take with these problems. So generally, mines are generally like 3 inches. That's their profile. And you want your frequency you want your target to be, electrically comparable to what your wavelength is for your operating frequency, right? So you just, in that case, we'll just pump up the frequency as much as possible to get as much, feedback as we need. But that's not the case because our soil is going to become more lossy as we increase our frequency, right? So it's kind of this give and take of, you want our target to be, in order to be sensed, we want this certain frequency, but we also don't want to go too high because then our soil is just going to attenuate all high frequencies, and you won't be able to sense it at all. So that's why S-band, C-band is generally what we see when we're looking at ground penetrating radar, which is kind of that give and take that happens. I don't know if that answered your question.
Yeah, that's good. Thank you.
Thank you.
I have two questions. First of all, how did you validate your method?
So the validation method that we used was using a moment method called discrete dipole method, which is just a moment method that it's just faster because these problems are very large. You kind of have to make some approximations even from full wave methods. It's basically impossible to just plug it into a straight method moments code. Then we ran we generated a bunch of surface realizations that met the specifications of our surface statistics, and then we averaged those results, those scattered field results, to get a mean RCS, which we then could compare with our method.
Okay. Second question, so the reflection is also affected by the roughness of the surface. Do you ignore it because of the losses, or just for the future you're going to add it? Or?
Yeah, so I think what you're referring to is that the
reflection from the
reflection
object.
from the object or the surface itself?
From the object that passes through the surface.
Yeah, so let me go back to a figure here so we can kind of see. Here we go.
Yes. Yeah,
Okay,
yes.
so we don't have any direct reflection from our target, if that's what you're saying. Like our plane wave is not unimpeded to our target. It has to go through our surface. So it's kind of a multi-layered problem,
Yes.
right?
But you only consider one way.
Okay, I see what you're saying. So you're asking, could second-order reflections ever happen in this case? That's a good question, and my answer would be yes. It is possible that you could imagine target geometries where second-order reflection could contribute. It would never dominate, since this first-order reflection would always be the dominant scattering. But second-order reflection could contribute, and I think for this method, you would just have to realize that that's an error you have to account for sometimes, right? It doesn't capture those higher-order interactions you target in your surface. Yes, that's a good point. Thank you.
Oh, I'm too short. Thank you for the nice talk. I had a question. First, it's not my field, so can you orient me a little bit and tell me what other people do to solve this problem and how you are competing and what the literature tells us?
Yeah, so the main problems with solving for the scattering of this nature is that there are two main problems which I identify here. Is you have to solve for this electrically large surface. You have to mesh it, and you have to solve for it. There are methods such as canonical grid method where you don't have to discretize your surface as finely. I've also seen in the literature, actually putting surface profile in the Green's function itself, which can, eliminate the need for surface meshing. And the other problem is how do you take the statistical results, because the only way that we really know at this point is just a Monte Carlo, various surface realizations, then back out the statistics. And there are other, not on the top of my head can I remember them, but there are some studies that are able to do that, but with this mesh surface, there's no studies that do both, right? There's no studies that say we don't need to mesh our surface, nor do we need to, remove the need for Monte Carlo.
And we probably don't have any more time. Okay. Maybe I'll catch you later. I'm curious about the dispersion because these are pulsed normally, right?
Yeah, absolutely. Thank you.
Thank you. Just want to make sure that I'm respectful for everyone's 20 minutes. So our second finalist is Mason Matrazzo from Auburn University. So let's come on up.
All right, I'm going to give myself a stopwatch so I don't talk too long. All right, my name is Matrazzo. I'm from Auburn University, and I'm a first-year PhD student. What's really funny about this is when we first started talking about me giving this presentation, my advisor was like, "Oh, don't worry, you only have to talk in front of a small group of like 15 people. It's really low stress." And for somebody that has an extreme aversion to public speaking, that made me a little bit happier. But as you can see, so just bear with me here. But yes, so today I'm going to be talking about parametric modeling and analysis of lightning spheric waveforms for D-region remote sensing. Yeah, so I think you guys probably heard a little bit about this earlier. We're going to go in a little bit more depth now. First, as I'm sure a lot of you in this room know, the D-region is a layer of the ionosphere that extends from about 50 to 90 kilometers in altitude. And it's a critical region for all sorts of RF propagation. It's affected by space weather. It has a big impact on VLF propagation, HF propagation, all sorts of things of that nature. So there's a lot of scientific reasons and a lot of practical reasons why we want to know what's happening in this region. So we want to perform sensing in this region, but due to its altitude, it's pretty difficult. It's too high for ground-based or like balloon-based measurements, but it's also too low to do like satellite and spacecraft-based measurements. So there's some challenges there, but there's some nice aspects of the way the D region operates that we can take advantage of to be able to sense this region, and that's where remote sensing comes in. So the D region and the Earth's surface form what is known as the ionospheric or Earth ionospheric waveguide, or EIWG, and you have this. It's like its name implies, it's a waveguide that propagates VLF waves with little degradation over long distances, hundreds, thousands of miles. And the nice thing is you can look at these waveforms and the characteristics of them, and you can, there's kind of information about the D region along that path of propagation that's encoded in those waveforms. So if you can extract information about those waveforms, you can kind of figure out what's happening in the D region along that path of propagation. So there's two major sources of VLF emissions that are typically used for these purposes. There's narrowband VLF transmitters. This is a pretty well-established technique for remote sensing that's been around for, I don't know, since the 80s or 90s probably. But there are some difficulties with using these transmitters. They're very large, they're very expensive, and they may not always be online. And another major disadvantage is that there's not very many of these. So you can see in the figure here on the right, there's a couple different naval VLF transmitters that are depicted there. There's also one in North Dakota that's sometimes online, but this is about all you get in North America that's reliably online. So you get some information about the D region, but there's a lot of spatial information that you're losing since you only get a few specific paths. So this is where spherics come in. So these are pulse space emissions from lightning strikes, and they emit a lot of very brief pulses in the VLF range. And the nice thing about these things, these emissions, is that they happen very frequently. So on a global scale, there's an average of over 40 lightning strikes per second. And as you can see in the other figure where, on the left, the distribution of these lightning strikes is all over the world. So you get a lot more unique propagation paths that you can analyze. So what's kind of the purpose of this presentation? So we have two main objectives. The first is that we want to develop a physically meaningful model for these waveforms, a way that we can express them mathematically. And then once we've done that, we want to show that we can extract information about variations in the D region from these parameters. So first, we're going to talk about how we actually collect the data. We use two orthogonal magnetic loop antennas using a receiver provided by Dr. Rob Moore, who was in the room earlier. He's probably here now. And it's located near Auburn, Alabama, out in the field. This is an example of the kind of antenna we're using, but this is clearly on campus, not out at the farm where the receiver is, but the same type of antenna that we're using. And then you can see here that we've got this raw VLF data that we're collecting. It covers a range of about 0 to 40, 45 kilohertz. So for the intents and purposes here, we want to extract just the spheric waveforms. So in these cases, any other transmitters are considered interference. So we're going to bandpass the data from about 3 to 20 kilohertz. This means that we get rid of the power line, 60 hertz harmonics that are down at the low end of the spectrum. And we also don't get signals from these VLF transmitters that I mentioned earlier. And the nice thing is that this little square range that's depicted here just happens to be the portion of the spectrum where most of the energy from lightning strikes is concentrated. And you can kind of see that by the little hump in the FFT. So then if you go to the time domain, you see these little impulse spikes. And we go through the data, we detect these spikes, and then since we have two orthogonal antennas with a north-south and an east-west channel, we can rotate these signals for maximum SNR. So once we've done all of that, now we've got, hundreds of thousands, even, millions over a couple days of spherics, but we need a way to mathematically express these variations in waveforms that we're seeing. So we did some experimentation with a couple different models, but this one is one that we found that works quite well. It's pretty simple, but yet robust, and it involves a logarithmic frequency chirp, which just, increases or decreases in frequency as time goes on. And then if you take that waveform, you multiply it by a scaled Rayleigh distribution envelope, so it's just a Rayleigh distribution, but the amplitude is just scaled up to reflect whatever the amplitude of the spheric is. So you take those two things, you multiply them together, and you'll see out pops a waveform which looks quite similar to the ones that you see over here, which is quite exciting. So the next reasonable question is, okay, how well does this actually work? So what we're going to do is we're going to perform optimization using nonlinear constraint optimization. Specifically, it's a modified version of MATLAB's fmin_con function. And we're going to do this for each of the spherics to find the optimal parameters that we're going to vary these parameters that I showed on the previous slide until the correlation between the original waveform and the reconstruction that we generate from these parameters is maximized. And as is usually the case with VLF-related things, it works better during the day than at night. But overall, you can see we took a couple samples, different times of year, different times of day, with tens of thousands of spherics. And the correlation between the reconstruction and the original waveform was quite good, usually in the order of 80 to 90%. So yeah, just as a summary, you take the raw data, bandpass filter, detect spherics by spikes in the time domain, rotate them for maximum SNR, then you define your model and you optimize the parameters with fmin_con. So the next reasonable step after that is you're saying, okay, now we have all these parameters. Can we actually learn anything about the D region and what's happening there from these parameters, or is this just a bunch of random parameter variations? And the answer is that you can actually get quite consistent and repeatable variations in parameters. In particular, we look at F0, which is the start frequency, the logarithmic chirp, and the sigma term, which describes the shape of the envelope that we're multiplying by. And as you can see, we get these on 3 different days in July of 2023. We get these pretty consistent diurnal variations. You can see the F0 is quite low at night, higher during the day, and kind of the opposite for sigma. And you also see these sharp changes right at sunrise and sunset, which is denoted by the vertical line. And again, that's what we would expect because the characteristics of the D region change quite dramatically as you go from nighttime to daytime and vice versa. We do see some variations again. This is again possibly due to variations in the D region, but also because the location of thunderstorms on these days, varies a little bit, so you get different propagation paths, different averages, so on and so forth. The next step that you would want to do after that is you want to take a known ionospheric disturbance, such as that caused by a solar flare. In particular, this is a really strong X-class flare. And if our model works well, you would expect to see changes in the D region and therefore changes in our parameters when the flare happens. So if you look over here on the left, you'll see that, again, we've plotted F0 and sigma, and we've also plotted the GOES X-ray flux for that day. And as I'm sure you can tell, that big spike in the mid-afternoon is when the X-class flare hits. And you'll notice that there's a sizable perturbation in both F0 and sigma. And if you plot this along with, I mentioned earlier, there's some well-established techniques for D-region remote sensing that involve tracking the phase and amplitude of VLF transmitters. So we compare both methods here. We take a look at the narrowband transmitter in Cutler, Maine, which is operated by the U.S. Navy with call sign NAA. And we plot its amplitude. At the same time, we also plot the just a zoomed-in version of that other plot, which shows F0 and sigma. And you'll see that if you overlay these two plots right as the flare hits, which is denoted by that vertical line, that's the peak intensity of the flare, you'll see that they line up quite similarly in both magnitude and time of recovery. So again, it's a very good sign that our parameters are giving us pretty accurate information about what's happening in the D region. And if anybody's familiar with the literature in this area, you'll know that a lot of people will isolate particular storm clusters. Up until now, we've just been looking at all lightning strikes, all spherics from all directions just to get overarching trends, which is useful for validating that this is indeed a viable method. But now we're going to take a look at specific source regions. The first one is down near Panama. It's this pretty nicely tight-knit cluster of lightning strikes, as you can see on the map. There's a little bit more widely distributed cluster near Mexico. And then we're also going to look at spherics from the northeast. So during the morning, you can't see it here, but those are mainly going to be from Europe. And then later in the day, you get these storms over here in the North Atlantic near Bermuda. All right, let me see if I can do a little pointer here. This is real small. I'm gonna try to do this. All right. So there's a lot to unpack on this slide, I know. So I'm gonna walk you guys through what we're looking at here. So over here on this side, this is what we've been seeing on the previous slide. This is all detected spherics on this date in November 2023. Again, you see we have a perturbation in F0, but interestingly, we do not have a perturbation in sigma. So we need to do some additional investigation to figure out exactly what that means. But over on this side, we're now plotting the same thing, zoomed in starting about 0500 UTC, but this time we're plotting the three different distinct source regions that I mentioned on the previous slide. So the first thing I want to point out is that there's these very sharp increases in F0 right here, and you'll notice that there's an increase in F0 from the Panama storm cluster quite noticeably before the storm cluster in Mexico. And again, this is what we would expect because sunrise happens in Panama prior before it happens to Mexico. You'll also notice that we don't see it's pretty consistent at sunrise here from this source location. And the reason that likely is again, you'll remember I said these are mainly from Europe at this point, so it's the middle of the day there. And the source path, even at this point, is still dominantly daylight, so you don't see those sharp changes as you go from sunrise to sunset like you see with these spherics. Let's see, what else did I want to point out? Oh, yes. If you look over here, we have another X-class flare that happens on this date, and you'll see, again, very sharp increases in F0, and you'll notice that F0 and sigma are pretty consistent during the day before you get to the flare. There's some variation right here. You'll see it's pretty consistent here, and then we get a drop. And again, that's what I mentioned earlier. That's where the source location switches from being mainly in Europe to the North Atlantic. So again, different propagation path, different D region characteristics. But you'll also notice that F0, there's sort of an increase, but it's not as defined as it is for the Panama and Mexico storm cells. You'll notice that the pink one is less defined. And again, this is because at that point, you'll recall most of the spherics are either in Europe or they're in the North Atlantic. And at that time of day, it's about sunset or past sunset at all of those locations. So there's not going to be very much effect on the nighttime side of the globe when you get a solar flare. So you wouldn't expect to see a dramatic change in parameters like you do for the daylight side of the globe. All right, so conclusions in future work. If you think back to those two objectives that I showed on the first slide, you'll see that we've met both of those quite resoundingly, in my humble opinion. And we've developed a model that can reliably describe 80%, 90% of the spheric waveforms that you're receiving mathematically. And then we've also developed, we've shown that these parameters actually give information about what's happening in the D region along this path propagation from source to receiver. Some of the future work that we want to do is, again, investigating exactly what these parameters mean physically. Like, what is F0 in terms of the Ionospheric waveguide? Is it the waveguide cutoff frequency? Something like that. We also would like to look and see what sigma is, exactly what that corresponds to. And then we would like to create a model that says, okay, when F0 is this and sigma is this, it corresponds to this exact characteristic of the D region. It could be reflection coefficient of the waveguide, something of that nature. And then also we would like to use multiple receivers. You'll notice that in this work we just use one receiver, but if you use multiple receivers, you get a lot more spatial coverage, and you can also better isolate by source location because you can do triangulation and time and angle of arrival, which is pretty useful. And again, I know I mentioned this before, but I just want to put a particular acknowledgement slide at the end. We want to thank the University of Florida, in particular Dr. Rob Moore, for the use of the equipment that he provided, as that was very integral to our work here. And yeah, any questions?
Excellent presentation. Nice job and very interesting work. One question that jumped out at me as I was looking at your loop antenna, I think that was on the campus of Auburn there. Nice picture, by the way. Did man-made electrical noise create a lot of problems for you, or did you place your antennas in a very quiet, electrically quiet areas? Because I've done a lot of VLF monitoring, and that's a real headache to deal with.
Yes, that's an excellent question. So this here is shown on campus. Obviously, that's not where our receiver is deployed. I don't think we'd want to leave it out in the middle of the campus green. That would be probably frowned upon by a number of people. But yes, this is out at the top secret location at Dr. Burch's farm, which is quite a ways away from downtown Auburn. And there the electrical noise is much lower. We do still have some problems with the harmonics. There's particular days that the data just hasn't been usable because there's been some weird spike in 60 hertz harmonics. But for the most part, we're far enough away from interference sources that we get very good quality data since we're out in the boonies instead of in the middle of campus.
Does your correlation process really reduce the effects of man-made noise, or just curious about that?
Yeah, that's a good question. By correlation, do you mean?
Well, you were synthesizing pulses, right? Matching to match data. Did I understand that correctly? Okay.
Yes, that's correct.
Did that have any noise reduction features to it?
We actually have talked about that, and that's another thing we like to look into in more detail in the future. I can't give like a quantifiable answer to that and be like, yes, it reduced by this percent. Hopefully it would, since it's designed specifically to reconstruct spheric waveforms, so it's more attuned to matching the particular shape that we see. In theory, I would think that could help reduce the effects of interference, but again, that's only going to be to an extent. If the interference is too much, it's just going to overwhelm the spheric signals. So yeah, it's a good question.
Thank you very much.
Thank you, I appreciate it.
On this same slide, you talk about using a passband in 3 to 20 kilohertz, and not going above 20 kilohertz because of those narrowband transmitters adding noise. I would imagine that on the time scale of a single spheric, the amplitude noise of any particular narrowband transmitter is relatively constant. Have you considered just subtracting that and extending your frequency range up higher?
That is also a very excellent question. So yes, we actually do have some methods for reconstructing the transmitter signal and just subtracting it out. That is still needs to be tweaked a little bit, and also the processing time that it takes to do this already is very long. Like processing a whole day takes almost an entire day of MATLAB plugging away. But when you plug in the reconstructing the transmitters and then subtracting them out, it takes infinitely longer. So in theory, yes, in the future, that is precisely what we'd like to do. We'd like to say, we're going to reconstruct the harmonics, we're going to reconstruct the transmitters first, we're going to subtract those out, and then we're left with just a beautiful spheric signal. That's the full frequency spectrum. Obviously here, we're retaining the part of the spectrum where most of the spheric energy is already, so you're not losing a ton of information, but yes, spherics are by nature wideband. So there's going to be some energy that extends above 20 kilohertz. So that is a superb question. That is exactly what we'd like to do in the future when it's a little bit quicker and we can, not have to wait weeks to process one day of data.
Yeah. And if I can ask a really short, separate question, I think I just missed this. How many parameters are you fitting for your waveform? You showed mainly 2, but how many parameters are you actually fitting to?
Yes. So I think we've got, I believe, 6. You can see them all here. There's the initial phase, the start and end frequency of the chirp. There's also the amplitude and then the scale parameter for the envelope. So it should be 6 parameters.
Okay, thank you.
So excellent talk. Thank you very much.
Thank you.
With the 2 highlighted parameters, F naught, but really sigma, that's really kind of almost a measure of dispersion, is it not?
Yes.
So it's how the frequency changes over time. And I wonder if you could talk a little bit about how one might expect a little bit of dispersion in the measurements that you're picking up in those spherics and why it might happen.
Yes, that is an excellent question. And this is something that we've just recently, right before Christmas break, we've started to really dive into this. Before this, I was just like, yes, this works it reconstructs the spheric very well, but I don't have an exact, physical understanding of what this actually means. So that's something that I plan to dive into in quite a bit of detail, hopefully in the coming year. I don't know if I can get, I can maybe postulate, but I can't. I don't know if I feel comfortable giving a very detailed answer to that question. But yes, in the waveguide, you would expect to have dispersion, different modes propagating, so on and so forth. And there's a very good chance that is what's being reflected in this sigma term. But yeah, we can talk about that in more detail later, and I would definitely love to go into that in more detail, in the coming months.
Thank you.
Thank you very much.
Our third finalist is Brenna Royersmith from University of Colorado, Boulder.
Okay. Hello, everyone. My name is Brenna Royersmith. I am a fifth-year PhD student here at the University of Colorado, Boulder, and I'm here to share my research in ionospheric tomography using unconventional GNSS signals. So I wanted to begin with a little bit of motivation of why do we care about improving imaging at high latitudes. The mid to high latitude ionosphere is very dynamic. We have auroral activity and particle precipitation driven by solar and geomagnetic storms, polar cap patches and smaller structures, just general magnetosphere ionospheric coupling that's driving a lot of charged particle movement and convection patterns and currents, informing even larger scale structures such as the trough, which I've done research on in the past. Basically, there are a lot of short-lived and rapidly evolving events that may not be predicted by current ionospheric models, but nevertheless have detrimental impacts on crucial satellite signals that we need for navigation and communication. So we rely on these observations and we can use them to study the ionosphere, but at higher latitudes, our data coverage becomes sparse. So these data gaps make it challenging to detect and monitor, forecast, and respond to events like this. So some current methods that can look at the higher latitude ionosphere include data assimilation frameworks, which also depend on data and can be computationally expensive, global ionospheric maps, and empirical and predictive models. A lot of common methods tend to rely on mostly ground-based data or GNSS radio occultation, or RO, for which I've plotted the coverage globally for on the right here. We have ground coverage shown in red, which is pretty dense and good, but restricted to land masses, and the cosmic 2 radio occultation coverage, which does give us over the oceans, but is restricted with latitude. Some expand to include ionosons or incoherent scatter radars, but those are also restricted to ground masses. So our key limitations are the sparsity of data over the poles and over oceans, limited vertical resolution of the ionosphere, and the fact that models may not be able to predict these little events. So what are we doing? We are combining the advantages of multiple observation techniques and in particular, some underutilized data sources, including GNSS reflectometry, GNSS-R, and low elevation signals, which I have more details on the next slide. We are taking these and integrating them into a three-dimensional ionospheric imaging scheme to expand our coverage to higher latitudes and give us better resolution and more accurate images. Currently, we are using a simulation for our technique to essentially make sure it's mathematically sound and test it out before bringing in real data and the noise that comes with that. So to summarize the sources that we are including in our study, we have ground-based data shown in red. This is just direct line of sight from a GNSS satellite to a ground receiver which has our dense network and high temporal resolution, but again is restricted to land. Newly, we have low elevation signals, which is still ground-based, but they are lower than about 30 degrees elevation, even below 20 degrees. Typically, these signals are thrown away because they have increased contamination from multipath and just extra noise, but recent research from my colleague Madeline Evans has shown that you can still retrieve precise total electron content from these signals with some special treatment. We're also including radio occultation. If you're not familiar, this is a signal from a GNSS satellite to a low Earth orbiting or LEO satellite. bending through the ionosphere with limb path geometry as the GNSS is setting or rising with respect to the LEO. We're also using POD, which stands for Precise Orbit Determination. This is similar to radio occultation and collected by the same satellites, but is a positive elevation from the GNSS direct line of sight to the LEO. And lastly, our GNSS-R, or reflected signals. This is signals transmitted from a GNSS satellite, reflected off a specular point, typically over calm oceans or ice, and retrieved by a LEO satellite. So these are all of the observational techniques that we are using to retrieve our total electron content, or TEC, and they each bring their own advantages, but what are we doing with them? We are doing tomography. And tomography is defined as the process of reconstructing the internal structure of a medium using multiple intersecting paths, but in our specific case, we're reconstructing electron density of the ionosphere using satellite signals. So the basics of our algorithm is that we have our simulated inputs, specifically the transmitter-receiver locations plus reflection points for GNSS-R, and the according TEC measurements for each signal. We then first load a background model. We are using the International Reference Ionosphere, or IRI, as sort of your initial guess at what the ionosphere looks like. We then construct our simulated truth, which is just IRI containing a Gaussian depletion to sort of mimic a trough or a bubble or some kind of structure that it did not predict. We then generate an inversion matrix, as we are doing inversion method tomography, which I have a bit more explanation of in a bit, to get a matrix of our ray intersections and invert that matrix to solve for our three-dimensional electron density and get these time-varying images at higher latitudes. So we are using a voxel basis for our tomography. A voxel is just an element of a three-dimensional spatial array. Think of it as a grid point like the yellow ones you see on the bottom right. We find the intersections of each signal path for all of our different signal types here with each voxel, and then update our base model image based on the data that we are measuring or simulating in this case. We are also using a uniform voxel grid, as geographic coordinates can tend to bunch together at higher latitudes or spread apart at higher altitudes, and this can create some ambiguity of like how many voxels your rays are intersecting or redundancy in your data. So we are instead using the universal polar stereographic system, which is on the top right. Next to ECF for comparison, this gives us a nice uniform box of ionosphere to reduce that ambiguity. Our current grid is pretty coarse. It's 500 by 500 kilometers horizontal by 25 vertical resolution, just for the sake of testing. And then it's hard to see in 3 dimensions, but we insert our Gaussian depletion in the center of this box to reconstruct. So our tomographic method is based on a previous pilot study from 2022 that has since been updated to perform a little bit faster and to accommodate the geometry of reflected data. Our voxel basis is applied to form a forward model, which is just the technical term for our inversion matrix, as we have this linear relationship between our electron density and our measured TEC. That is, TEC equals H times NE, which is our electron density. Think of this as a simple Y equals AX equation where you want to solve for X. And that big H matrix in the middle is the one containing all of the intersections and contributing lengths from our signals. So the forward model is developed using Bayesian-Voronoi tessellation theory. This is just mathematical theory to calculate, contributing intersections from your data. And it was chosen because it is versatile, adaptable to different grid types, and it is pretty quick and iterative for calculating that. To then invert this equation and solve for our electron density, we use the simultaneous multiplicative algebraic reconstruction technique, or SMART, that just solves that equation. We use this because it is multiplicative and updates to preserve positivity, simultaneously updates all of your voxels, and has a low sensitivity to your initial guess, so you have more reliance on your true observations. It is faster and more stable than its predecessors, ART and MART, same acronym, less words, and assures your non-negative solutions as long as your system is non-negative. So input into our simulation, we have a total of 78 GNSS satellites from the GPS, GLONASS, and Galileo constellations, with all the proper orbital parameters used to ensure that this is as realistic as we can possibly make it. Our Leo constellation is simulated inspired by the Spire CubeSat constellation, as these are polar orbiting CubeSats that get our high latitude resolution, but are also likely the source for reflectometry that we will be using with real data. Then we have redundancy reducing further in our signals using the dot product greater than 0.75. The point of this is basically to say if you have a ray and one slightly askew from the next step, that's going to be a little bit redundant and not contributing anything new, so get rid of it to not bog down your system too much. Our Leo CubeSats here are used for radio occultation, reflection, and for POD out of convenience, but they also do provide those products at Spire. And our TEC simulated data is found by using that y equals hx equation straight through, solving your TEC using our matrix and multiplying it by our truth model. So the output of our algorithm is a three-dimensional image of electron density, but that's a little hard to interpret visually. So I've instead taken slices in each basic direction of the UPS coordinate system. So for each row, the first one we have along the easting direction in the center, in the middle along the northing direction, and on the bottom along altitude. That's just if you sliced it like a hamburger bun, just right in the middle. In our columns, we have our IRI truth model, our reconstructions with and without reflections, and our errors with and without reflections as well. Here we have defined error as the difference between our reconstruction and the truth. And it is a lot to visually take in, but I just want to sort of highlight here mainly that we, A, can successfully reconstruct the electron density. B, the most errors tend to occur in the middle where we've placed this depletion. This is expected as it is not, expected by the model, and we are updating an image to get there. It's not 100% perfect, but we can get pretty close. And to mostly, above all, show that the errors with reflection are noticeably lower and darker than without reflection. Sorry. If you're more, firstly on the top, I had a three-dimensional plot of the error here as well, just to show how that Gaussian blob occurs like right in the middle and creates most of the error, but it tends to congregate on the bottom due to our topside radio occultation and POD coverage, just if you wanted a three-dimensional output example. And if you're more of a numbers person to see how these errors improve with reflections, we have a table. In each row, we have iteratively added 5 LEO satellites to see as we add more data, more satellites, more reflections, more ray pads, how those errors reduce. So I've highlighted in the second two columns, we have the root mean square errors and the mean errors with reflection. Those are highlighted in green, and the RMSE and mean errors without. And the main takeaways from this is that our RMSE improvements overall with reflection are about 23% in contrast to 4% without, and in mean errors improve by about 58% versus 38% without reflections. And the last column, the mean difference, just means the difference in the reconstructions with and without reflection to show how different those results really are. So knowing that as you add ray pads and satellites, you get more intersections, how specifically do these data types contribute? So on the left, I've plotted these two histograms. The one on the far left is the number of voxels with that number of intersections, if that hopefully makes sense. And next to that is the number of voxels with the intersection lengths contained within them. And on this, I have plotted in red results using all of our signals, including GNSSR and low elevation. In blue and purple, the cases without them individually, and in green, without either reflection or low elevation. And the main highlight from this plot that I'd like you to take away is that without reflection or low elevation, we have more voxels with less intersections and less lengths. We are basically getting less contributions from our data, versus when you include more data and you get to red, including all the sources, we have many more voxel intersections and more contributing lengths and more things that we can update our image with to better reflect the ionosphere. And so what exactly do more intersections mean? On the right, I have chosen one voxel in particular. This was the voxel with the most intersections. And I studied that, adding ray paths about 100 at a time to make it not too cumbersome, adding ray paths iteratively to the reconstruction to see how is this voxel's electron density changing as we add data to it. So on the bottom is plotted in blue the reconstructed electron density, and on the bottom in pink is the truth model electron density, which is not changing, that's just from IRI. And then in red behind the reconstruction, this is using a different y-axis. It's the error, just to ensure that it is changing in the same fashion. And around 18,000 rays into the reconstruction, we get ray paths that are intersecting that voxel and thus updating it, getting iteratively closer to the truth, which is exactly what we want, and it's great to see. So basically, in conclusion, we have this algorithm that is capable of using reflected signals, and it works effectively and can produce those reconstructions. We see that GNSSR and low elevation signals do substantially contribute to the algorithm and minimize our errors and help us look at the high latitude ionosphere in better detail. So having a validated algorithm using simulation that helps set us up for real data integration in the very, very near future and hopefully makes the transition smooth. So that's about it for me, and thank you so much. I'll take questions.
Hi, I really liked your talk.
Thank you.
I have a question. When you have the matrix H,
Yes.
will you have any issues if the determinant of that is near zero? Have you experienced anything like that?
I have not experienced anything like that, so I don't know off the top of my head if that would be an issue, but as far as I know, it's not something that we would encounter.
Okay. You might want to think about that because that makes the matrix ill-conditioned, and
Yeah,
then I
absolutely.
wonder what happens.
Absolutely, thank you.
I have a question, might be very obvious, but it's not my field. So you
Totally
have
fine.
multiple sources, like different satellites. How do you synchronize them?
How do you mean synchronize?
Like, do you have a timestamp, like the signal that you are looking at, that they are all referring to the same?
Yeah, so multiple of the sources do require, that geometry lining up, especially reflections have a lot of different factors. So it's not always a guarantee that we will have, all those data at the same time. That's, the benefit to using simulation is we can be very optimistic and say, yeah, these are absolutely all happening in the span of 10 minutes. But that is a factor in our moving towards real data, having to nail down, does this day have coherent reflections that we are able to use? Is there available radio occultation data? It does not always line up, and you can't assure synchronization, but it's, we do our best, and it is available pretty much daily, the sources. So
when you have the real signal and you mix them, you might get more error than less error. I mean, now it's very idealistic, right?
yeah, it definitely would vary for sure, how much data you have each day. It wouldn't be perhaps a consistent amount of error. I would say more the hope is that we can get as much as we can to get as close to an accurate ionosphere as we can, something that's just, more accurate than a model, ideally.
Thank you.
Yeah.
Thanks for your presentation. It occurred to me that I wonder if you have any thoughts about whether what low rank approximation of your model might look like, and what that might mean physically, if you might be able to break your data up into some kind of minimal set of signals that you need to get a good enough approximation for your model.
Oh, basically, if I'm interpreting you correctly, is assigning like a threshold to say, hey, once we have at least this many satellites or this many ray paths, that gives us a pretty substantial error?
Essentially, yeah. Or,
Okay.
well, my instinct is whenever I see a big matrix, I say, okay, singular values, what do you get out of that?
Yeah,
essentially?
I unfortunately do not have that, but I really like that idea, so I will be taking that with me. Thank you.
Well,
Time's up. Okay. Thank you.
All right, our fourth finalist is Ashwyn Sam from Stanford University.
Good afternoon, everyone. Before I get started, I want to do a quick poll. Who here uses either Google Maps or Apple Maps on the regular? I can't seem to get around anywhere without using it. All right. And who checked the weather app at least once today? I'm from California, so anything below 60 degrees and I'm checking obsessively. All right, seems like many of you in the room. Even for those of us who work in this field, we rarely stop and think about how much of our daily routine, GPS, weather, communication, finance, etc., depend on satellites. And space technology has become core infrastructure that we take for granted. And unfortunately, there is a threat to all of it, and most people haven't even heard about it. This threat is what I want to talk about today. My name is Ashwyn. I'm a PhD student at Stanford, and today I want to tell you guys the problem of small space debris and a potentially new way to detect them. These images were unveiled by President Biden in 2022. They represent the deepest and sharpest images of the distant universe. I'm sure you've seen them because when it first came out, this is all that the internet could talk about for a while, and I, like everyone else, was in awe of it. I found it beautiful, inspiring, and as an aerospace engineer, I was reminded of the vastness of space and our future in it. These images were taken by NASA's James Webb Telescope that continues to be in orbit and continues to take these on-inducing images. But here's the thing. These images almost did not exist because this spacecraft almost completely failed within just a few months of flight. And that's because it kept getting hit by micrometeoroids and created hypervelocity impacts. And these collisions created permanent damage on the spacecraft and almost completely took it out. I want you guys to take a second to internally guess how much money NASA spent on this project and therefore how much money could have been potentially lost. I was shocked to find a total of $10 billion could have gone down the drain due to these collisions. And this threat to the safety of spacecraft is not unique to James Webb, nor is it unique to micrometeoroids. Man-made space debris can have the same effect. In fact, every single satellite that is in orbit today and will be in the future is constantly under threat of coming into a fatal collision with one of these objects. And I don't need to stand here and tell you guys about all the utility that space technology offers our lives on Earth right now. And I'm sure that you guys, like me, are excited about the future space economy. But that economy will not arrive if we don't deal with the existential threat posed to it by debris. And unfortunately, there is a lot of it, and it is only growing exponentially. As you can imagine, when debris makes collision with an object, it creates more debris, more collisions, more debris, and the cycle grows exponentially. This is known as Kessler syndrome. And when Kessler first predicted this many decades ago, he warned us that if we don't deal with this soon, then eventually there will be way too many objects in space, and space itself could become unusable. So everybody agrees that debris in space is bad. But it is especially dangerous when you cannot even detect it. And this is the case with sub-centimeter-sized debris, or what I'm calling small debris. We have ground-based radars and optical methods to detect debris that's larger than a centimeter or so, but when it's smaller than that, we just can't see them. But like the quote on the bottom there says, we estimate there to be over 100 million of such objects, and even a small one like a paint chip off of a satellite moving at 10 kilometers a second, getting hit by one of these is unfortunately equivalent to getting hit by a 550-pound object moving at 60 miles per hour. This could be fatal to your multi-million-dollar spacecraft. To illustrate this point a little bit more, I have this screen recording of me playing around on this website called Leo Labs that allows you to track objects in LEO. If I zoom in over America, the objects in green are payloads that we can track, and the objects in red are larger debris fragments that we can currently track. But if I zoom out and now turn on the debris fragments, the small ones that we cannot track, these are estimates, we see just how much more dominating and overwhelming it is. It creates this shell in LEO, and surely you understand that this is a problem. And so scientists and engineers have been trying to devise new and clever techniques to try and detect these smaller objects. And one such idea is to take advantage of the fact that there is a lot of plasma in space. And as the debris moves through the plasma, it can get charged up. And a charged object moving through a plasma can create interesting waves. More specifically, it can create something called a soliton. To explain what a soliton is, I want to bring your attention to this video on the left here that shows a boat moving through a channel of water. It turns out that if the boat moves faster than a special characteristic velocity of the water, then the waves that the boat creates can detach off of it and propagate ahead of and faster than the boat itself. If you look really closely, you see these two hump-like structures that are propagated ahead of the boat. Those are solitons. They were discovered in water, but they're not unique to it. This video on the top right is a simulation I did of a debris moving through a plasma from left to right, where the red vertical line represents the debris position and the blue represents the background plasma density. And we see here that as the debris moves, it creates these perturbations that form into these solitary wave structures that have propagated ahead of the debris. These are solitons. More specifically, they're precursor solitons because of its ability to move ahead of its source. And this idea was validated experimentally by a team in India where they ran plasma over a charged wire, and they did in fact find these solitary wave structures that moved in the upstream direction. That's the image on the bottom right there. From a more fundamental standpoint, what's happening is that these are nonlinear waves, and their nonlinearity creates a tendency for the waves to grow and steepen in amplitude. But they also have a dispersive force that creates a tendency for the waves to spread apart and disperse. And there exists a scenario under which these two counteracting forces creates this beautiful mathematical balance that creates this harmony that allows for these waves to propagate large distances without distortion to its shape, speed, or amplitude. And so the idea for us is, well, these debris, they're too small to be seen. But if they generate these solitons that can propagate large distances, and if we can detect these solitons, then we can hopefully, therefore, detect the debris that created them. This idea has been gaining attention in the last couple of years in the orbital debris community, but there is a potential flaw to all of this that has garnered a lot of debate, and that is, will Landau damping kill away the soliton? Now, I'm assuming that most people in this room know what Landau damping is, so I will briefly only describe it as a collisionless damping mechanism that transfers energy from the wave to resonant particles, thereby decaying the amplitude of the wave. So the question I tried to answer in this talk is, does Landau damping kill the soliton before it serves any practical detection purposes? I must also note that here I'm specifically talking about ion Landau damping, which occurs when the ion temperature is on par with the electron temperature, which is a realistic condition. There are currently three main ways to model a soliton. First, you have analytical methods, which are important because we're trying to study these solitons over such large time and length scales that it's computationally not practical to try and simulate every aspect of this. And so analytical models are important. In fact, the seminal papers in this area and the bedrock upon which this field has emerged has been on a couple of analytical models, namely the Korteweg-de Vries equation. Next, we have fluid simulations, which are also where you solve the fluid equations. These are really good, but if you want to study something like Landau damping, which is a kinetic effect, then the gold standard for us would be to do kinetic simulations, and that's what we chose to do in the study. I do the particle and cell, or the PIC technique, where you scatter charged particles onto a computational grid, and based on the relative positions of these particles, you can calculate an electric field and a magnetic field by solving Poisson's equations if it's electrostatic, or Maxwell's equations if it's electromagnetic, and then based on these fields, you then push these particles into new positions and new velocities, and then run the cycle all over again. Mathematically, you're solving Vlasov's equation, which describes the evolution of the distribution function. Our choice of software here is Warpets, which is an open source code from Lawrence Berkeley National Lab. I love Warpets because it's really great because it's highly optimized, including the ability to run on GPUs, which has made my life so much better because I found that solitons are extremely sensitive to noise because this noise acts like numerical collisions that can damp out the soliton. So in order to minimize this effect, I had to use a ridiculously high number of particles, including in 1D, I'm using over 1 billion particles. And so to keep all of this maintained well, I had to use something that's optimized, and Warpets manages that really well. The way I set up my simulation is with a soliton already initialized in it. So I just launch a soliton into a plasma and then observe its evolution. So I want to emphasize here that I'm only studying the soliton's propagation, not its formation. I initialize the soliton. These are 1D studies where I initialize the soliton according to the solution of the Korteweg-de Vries equation, which is this hyperbolic secant square profile shown in that fourth bullet point. I set the ion density, electric potential, and velocity according to this, and those initial profiles are shown on the right there. And I run multiple simulations where I vary the initial amplitude and also vary the ion to temperature ratio, and I picked plasma parameters that are representative of Leo plasma conditions. As a frame of reference, I want to first show you guys a result of what happens if I run the simulation with the ion temperature set to be exactly 0. That's that movie on the top left. You see the soliton evolves from its initial state by shedding off some wakes as it moves to the right, and eventually it reaches a saturated state. The movie on the bottom left is the electron phase space. I know it's a little bit hard to see, but if you look closely, there are these vortical structures that form that are indicative of electron particle trapping. I want you guys to keep that effect in mind because I'll come back to it later. And on the right, you see the evolution of the soliton until it reaches saturated amplitude. These cold ion studies are great because it shows the existence of solitons that can propagate without damping, and we did a very deep dive into this and published a paper on this in Physics of Plasmas if anybody's interested in reading about it. But what we're currently wanting to look at is what happens when you have thermal ions. So here I'm showing an example of a simulation where the ion temperature is set to be the same as the electron temperature, and I initialize the soliton with an amplitude of 0.5. That's what's shown in the blue there. That blue soliton, after some time, decays into the red, and after even more time, decays into the green. So clearly, we see heavy damping here. But what we found that I think is very interesting is that that green soliton, shown in the zoomed-in inset, is actually a saturated state, meaning it maintained that shape and amplitude for the rest of the simulation. And we ran it for a very long time, much longer than I show here, and we found that it maintains an amplitude about 1% till the end. And this is important because this 1% amplitude is still technically above the detection threshold, meaning in theory, even these heavily damped solitons can be detected by onboard sensors like Langmuir probes, for instance. We can then compare this with linear theory by looking to the kinetic dispersion relation for ion acoustic waves, shown over here, where z is the plasma dispersion function. We numerically solve this for omega, where the imaginary component of omega gives us the damping rate. That's what I do here. I solve it for various wave numbers and different temperature ratios, and clearly we see here that as the temperature ratio goes up, so does the damping rate. I then translated all of that into the damping of the soliton shown in this movie on the right. The way I got this is slightly non-trivial. I had to take an FFT of the entire soliton to find all the relevant wave numbers because the soliton is a superposition of many different wave modes. And for each of those wave numbers, there is a corresponding damping rate given by the dispersion relation. So I then apply that damping rate to each mode individually and let them damp independently in spectral space. And then I transform it back into physical space by doing an inverse FFT, and that's what's shown over there. This allows us to track the amplitude of the soliton as a function of time as predicted by this linear theory so that we can then compare that with what our PIC simulation gives us, which is shown in blue, and the theory is shown in red. I do this for the example here for temperature ratio of 1 for 3 different initial amplitudes. We see here across the board, we don't really have good agreement, especially at smaller amplitudes. We see worse agreement. At larger amplitudes, it's better. But the important result here is that there is a saturation to a non-zero amplitude. And if I do this with different temperature ratios, we once again see poor agreement, especially at the smaller values. Now, there's an important caveat to all of this, which is that by thermalizing the ions, I'm also introducing a pressure gradient that creates this force that will want to flatten out the soliton and decrease its amplitude. This is a fluid phenomenon that's not modeled in the linear kinetic theory, so we weren't really expecting these to match anyway. But what's interesting is that if anything, this fluid phenomena should only increase the damping, but we find here reduced damping and a saturation. So this question that I set out to answer, does Landau damping kill the soliton? We find from our simulations not quite. It does decay, but doesn't completely go all the way down to zero. But why though? This is what I hope to answer in the next couple of slides. This is an interesting result because when we look at the linear theory and its ability to predict the soliton amplitude, we see that it matches better for larger amplitudes and less so at smaller amplitudes. And this is interesting because it's counterintuitive. You would think that linear theory is better able to predict smaller amplitudes. But this reminded us of a different result that we had published in another paper, where we showed that trapped electrons introduce a new nonlinearity that can relatively play a larger role at smaller amplitudes and create a larger deviation from linear theory. And we see the same pattern happening here, so that prompted us to look once again at the trapped electrons. So to do that, I look at the phase space of the electrons shown in this movie here, and on the right, I'm just showing some snapshots so you can see it a little bit clearer. But in this phase space, there are electrons that are either trapped or untrapped. How do we know which one is which? To do that, I overlay the phase space with contour lines of total energy. If the total energy is positive, I represent them with a solid line. If it's negative, it's the dotted lines. And where it's negative is where the electrons are trapped. This now gives us the ability to categorize electrons in both velocity and position as either trapped or untrapped, so that we can then isolate just the trapped population and do a deeper dive into just those electrons. So that's what I do in the next slide here. I look at the total energy change for all the different species from the start till the end of the simulation. We see here that ions have gained energy, which makes sense because the soliton, as it moves, it accelerates the ions. The electrons have lost energy, and so has the field, and overall they all add up to conserve energy. But here's the interesting thing. We found that actually 83% of the energy that the ions gain come from the electrons. And this was surprising to us because when we first started on this project, we were so confident that the two main players in this energy dance would be the field and the ions. But we find that the solitons play a much larger role in all of this than we had initially expected. And if we look at the evolution of the trapped population's energy over time, shown in the red there, we see that it does in fact go down and it saturates. And if you look at the soliton's width in the blue, it also evolves and it also saturates to a finite value. And interestingly enough, they both saturate at the same time. So there seems to be some sort of a correlation between the evolution of the soliton and the trapped electrons. And so I think it's fair for us to conclude that the trapped electrons seem to play a larger role in all of this than previously expected. So going back to this question of why does Landau damping, why does it get arrested, I think it's because there's some sort of an electron-mediated energy transfer that balances out this damping. And the reason I say we think is because, well, more evidence would need to be collected to make this a more robust argument, but I think I've shown enough evidence that this at least warrants looking into this further, and I think we would find some interesting results here. The last thing I want to conclude with is proposing a new type of analogy to think of Landau damping of solitons. Our results reminded us of an adiabatically expanding gas in a piston cylinder system where as the piston expands, the gas inside cools down as it does work on the piston. And for us, as a soliton expands, the trapped electrons cools down as it does work on the ions. And we even found that the adiabatic relation of temperature times volume to the gamma minus 1 is in fact held constant if we assume a gamma of 1.63, which is within the expected range of values. And with such a framework, I think we can, hopefully it'll be helpful in future studies of Landau damping of solitons. The main takeaway from all of this is that small debris is bad because it's hard to detect, but hopefully solitons can help with that. And Landau damping potentially kills it, but we're showing here that it doesn't completely kill it to zero. It still maintains a detectable amplitude. And the reason we think that's the case is because there is an electron-mediated energy transfer that halts the damping. And hopefully by understanding these physical processes better, we're one step closer to solving the small debris problem so that future generations can also use a GPS, check their weather, and take space for granted just like we do today. Thank you.
Hi. Well, nice work and nice presentation.
Thank you.
Can you give an example of a technique for actually measuring the solitons?
Yeah. So there's not much literature on this topic. It's a very new field. So there's only like 6 or 7 papers in here, but the one paper that does mention this talks about how for lower LEO portions, we actually don't see these precursor solitons in the simulations that they did. They get something called a pinned soliton that moves with the debris, and those solitons, they say, can be detected with ground-based radars. For above that, I think it's above like 700 kilometers or so, then they found in their simulations that they do in fact see these sort of precursor solitons, but those can only be detected with onboard sensors.
Right. So what kind of onboard sensors?
The paper that they cite only talks about Langmuir probe, so that's the only thing I can mention, yeah.
Yeah, that's where I was going. I think Christina Hartzell.
Yes, yeah, the Hartzell and Truitt paper is what I'm talking about,
Yep.
yes. Yeah.
Thank you.
Yeah, you're welcome. Thank you.
Two related questions. So I think I understood you said in the PIC simulation you see remnant signal and in linear theory doesn't, right? Have you checked that that's not a numerical noise effect at all?
Yeah, so every time I do simulations, numerical noise is the crux of it's a thorn in my flesh. And so I always try to do as many convergence studies as possible where I increase the number of particles, I increase the resolution until I make all those effects disappear. So I'm pretty confident that the number of convergence studies I've done gives me confidence that they're not numerical effects. Yeah.
Okay.
But you never know, yeah. But
Second, I think you were saying that maybe the ions are damping the electrons, maybe enhancing the wave, right? Usually in plasma physics, whether you get damping or growth depends on the initial distribution of those particles, right?
Yes.
Did you mention what those were?
No, good question. I did not mention. These are Maxwellian distributions. I didn't initialize the electron distribution to be trapped when it starts, but the PIC simulation automatically reaches that state. So I didn't need to initialize some sort of a BGK mode or something. It automatically goes into this trap state. Yeah.
Sure. So if I understood this right, I think what your talk was about is Landau damping doesn't kill it, it takes it down to 1%. and then it stays there.
Yes.
Do you have, and maybe this is more a question for someone else in the audience, but do you have a way to test this in a laboratory that you would feel comfortable with? Like, what's the next step to see if this is real? Not in simulation, but
that's
real.
a great question. Unfortunately, I'm only a computationalist, so maybe people in this room can help me share their expertise in helping me come up with an experiment for this. But I think maybe some sort of a lab experiment, but where the plot I showed for the team in India, where they had plasma flow over a charged wire, and they did in fact find these solitary wave structures, but it didn't run long enough for them to see any sort of damping. So maybe if we can have some sort of a closed loop where the solitons just keep propagating on its own, and maybe we can observe how it damps and things like that. That's the best guess I have. Yeah, but thank you.
All right, our last finalist, Sarah Tanvir from University of Wisconsin-Madison.
Hello everyone, I am Sarah and I will be sharing the propagation measurement that we did in the 7 gigahertz band near the VLA telescope. So firstly, I would just like to describe what the VLA is. So as the name suggests, these are very large telescopes, and there are 27 of them arranged in this Y-shaped track. And these tracks are used to move the telescopes closer together or further apart from each other, depending on the measurement that they need to take. And these telescopes are mainly used for radio astronomy, which means that they need to collect signals from far away space objects, and as you can imagine, these signals will be extremely weak. Therefore, the telescopes themselves are extremely sensitive. Due to this, this makes the telescopes even more susceptible to interference with any signal that is generating from Earth, as obviously any object on like Earth will be closer than a space object. So such signals can completely mask the measurement that they need to take. So for some context, the threshold for these can be as low as minus 250 dBW, which for further context is about 1 billion times lower than the average receive power for your cell phone, for example. So they are obviously extremely sensitive. So since they are so sensitive, how do they deal with interference? Because obviously it will exist. So there are a few different ways that we do this. So one is that they often operate in protected bands. However, not all bands that they collect in have these protections. Another way is to establish radio quiet zones, which are zones where the transmission of signals is greatly reduced. However, the VLA itself is not in such a zone. So now that we have a part of the frequency spectrum that we have to monitor that is not protected, and we are also not in a radio quiet zone, the only option that we have left is to share the spectrum with other users. And this is what we will be focusing on. And let's take an example of such a band, which is the 7.125 to 8.14 gigahertz band. So currently there is no protected band for radio astronomy in this band. And the other users mostly consist of point-to-point fixed links as well as weather satellites. And they share the band mostly on an opportunistic basis, which means that they kind of try to work around one another. So how does the VLA, which is much more sensitive to interference, deal with this? So right now, part of what they do is to follow a strict schedule. So let's take the example of the other user in the band, which are satellites. So the set of satellites that can interfere with the VLA is quite small, actually, and using public knowledge, they can predict when these satellites are scheduled to predict, and then they can basically pause measurements to avoid interference. And then once the interfering source is gone, they can continue as usual. Whenever this method does not work, they can also simply detect the segment where they saw that the measurement was interfered with and perhaps discard it. So if we know that this is working well enough, why are we even talking about this band? So the answer is 6G, which I think we have all discussed quite a lot in the past couple days. So this band has been identified by the WRC-27 as one of the bands where 6G is trying to move into or can potentially move into. And then there are a few different reasons for this. Just to keep it short, one, it will be quite scalable for them because they can simply reuse base stations that do exist already. This is one of the few bands that is universally available in a few different regions. And this band can basically give them the coverage as well as the capacity that they need to transmit data more efficiently. So what will the impact for the VLA be if this new user does move into this frequency band? So here, let's revisit the diagram that we saw earlier, except this time we have some new users here. So the first is, we can see the ground station, and we have some users that will connect to this ground station, and then obviously there will be some cellular signals in this band. So the main difference between this new user and the older users is that once, like I said before, the satellites are easy to predict. However, human beings do not come with TLEs that we can use to predict their motion. So this will be more unpredictable. And during scheduled measurements, the signal might be interfered with. So the previous paradigm of scheduling might kind of fall short in this situation. So to characterize interference, Spectrum X conducted the first ever transmit experiment at the VLA. And here I would just like to pause and give thanks to the entire team who helped conduct this experiment. So now let's get into the experiment setup. This is a simplified diagram. So here in the Y-shaped tracks, we have the VLA telescopes, and at the southern corner, we have our receiver. There were multiple transmitters. However, the one that I will be focusing on is the one that was moving down the highway north of the telescopes, because this is basically simulating a user that would be potentially using this band. And both of these devices were custom made by Spectrum X to conduct this experiment. So what I want to measure is what was the maximum distance at which the signal was still detectable, and additionally, how does the SNR vary as the distance between the receiver and the transmitter changes. So let's keep these two questions in mind as we move on. So here was the structure of the signal that was transmitted. So first we have the 6G-like uplink signal that was just a 5G signal replayed in the 7 gigahertz band. And secondly, we have the modulated part of the signal, which is the one that I will be focusing on. And this is basically trying to serve as a beacon of sorts so that the telescope can be able to identify that signal can potentially interfere. So this is the beacon that I will be analyzing. So to do this, I first had to isolate this tone from the rest of the signal. So I did this simply using GNU Radio, and I used a low-pass filter to center the beacon and just extract the usable part. So this is the beacon that we will be analyzing. And here we can see the before and after signal processing. So here we have a video of the motion of the car as it transmitted the signal. So if I can replay it. So the car moves northwest away from the telescopes, makes a U-turn, and then comes back. And here we can see how the SNR changes with respect to the location of the transmitter. So first, let's talk about what makes sense. So nearer to the telescope, we can see that we have quite high SNR, which I think makes sense. However, at the start of the journey, we can see that the SNR is actually quite low, which was surprising to us. And upon further analysis, we concluded that this is because of the actual structure of the telescopes, which are basically blocking the signal. So which is why we have low SNR at the start. And to further analyze this, I have this scatter plot. So on the y-axis, we have the SNR, and then on the x-axis, we have the distance between the transmitter and the receiver. So at the start, we can see that the SNR is quite high when the distance is small, so this is expected. However, then we see a sharp drop, and this region is where I think the telescopes start to block the signal. And then after this, we can see this kind of oscillating effect. And this is due to the shape or the distance between the telescopes. So we have one region where the signal will be blocked due to the structure of the telescope. And then we have some region where it's like empty space. So that is where the SNR increases. So I hope this makes sense. And to the main conclusion that I want to reach with this plot is that there is a complex pattern of propagation due to the actual structure of the telescopes themselves. So next, this is the actual signal that was received by the receiver. So first of all, I would like to note that we did see the signal for the entire time. So even up to like around 15 kilometer distance, we were able to see the signal. And however, we did transmit a constant frequency tone, but here we see some frequency shift happening. So this is consistent with the Doppler shift that we would expect from a car that was moving around 100 kilometers per hour. And so if we go section by section, we can see here that there's a negative frequency shift, which means that the transmitter was traveling away from the receiver. Here we see it jump up, which means that this is where the U-turn happened and the direction of the transmitter changed. And then here we see the 5 minutes where the car actually stopped to take some pictures of the telescopes. So here we see no frequency shift. And then lastly, here is where we returned back to the telescope. So with this plot, the conclusion that I want to reach is that the motion of the cellular device will actually cause Doppler shift, making just adding one more layer of complexity to the potential interference faced by the VLA. Therefore, we need even more measurements to characterize the impact that 6G may have on radio astronomy. So to extend this work, I would like to analyze the data from the other transmitters as well as the other parts of the beacon. Secondly, the telescope itself was also collecting some measurements during the experiment, so it would be interesting to note what the data says from that. We have done some cursory glances over it, and a similar propagation pattern did emerge. And lastly, since the physical structure of the telescopes are kind of affecting the SNR, perhaps it would be interesting to repeat this, but with different configurations of the VLA. And that is all from me. Thank you. Any questions?
Two questions. First of all, I mean, in your VLA, you have multiple receivers. Wasn't it possible to find the location of the transmitter and cancel out the effect?
So for the receivers that we had, not the actual telescope, right?
So the VLA has multiple antennas.
Yes.
Don't you have access to each signal? And then based on that, you can calculate the location of the transmitter and cancel out the effect of that?
Yeah, so I think that will definitely be possible, and perhaps one way to extend this work. However, as I did note, the Doppler shift might make this a little bit more complex because it will not be like super easy to track the signal. But and currently, what we analyzed was just based on a singular receiver, just as like an initial study. So I have not actually looked into mitigation techniques yet. But yes, thank you for your question.
So you did one simulation, like one incident of this path, right?
Yes.
Do you think you can make conclusion based on this one set of data?
Yes, I think repeating it definitely holds merit. And the entire measurement did take a long time, and it was quite complicated to set up. And I know they had like little time and everything. So I think definitely like we need to do this multiple times, especially using different configurations of the telescopes. Yes, thank you for your question.
No, excellent talk. So you just basically drive tested a CW transmitter in motion and then received it at a fixed location.
Yes.
Couple of suggestions is that you, first of all, with your transmitter, use a frequency reference. You can measure Doppler spreading, and also with that, you can also look at the K factors and things of your radio channel. CW is a very powerful measurement technique. And also, you might want to calibrate it for path gain or path loss. You could do that, enhance your measurement procedure to do that. But and also, I think as the other researcher mentioned, you could use multiple receiving locations as well to enhance your measurement. I was just curious as what the source-victim scenario that you're looking at. What you placed it right behind one of the VLA antennas or near that. What was the problem you were trying to solve there? Or are you just trying to build an experimental methodology to answer a more general question?
Yes, thank you for your question. Yes, just to clarify, right now we are just trying to kind of characterize what the effect will be, since this kind of study, at least to my knowledge, has not been done yet, especially in this particular band. So this was more just like a setup to a larger study that hopefully we are planning on collaborating with many different universities on. Yes, thank you.
Thank you very much. Nice talk.
Thank you for your suggestions as well. I will definitely keep them in mind. Okay, thank you, everyone.
All right, so this concludes the student paper competition. Congratulations to the 5 students who made it to the finalists, who had 30 applications this year. Thank you to everyone for attending. Stay tuned. At 6:30 today, we have the reception. We're going to announce the results. And last thing for the judges only, we're meeting on the 2nd floor right after this in the Flagstaff room. I know some of you have commitments, so if you need to go, please make sure you leave the form with me so I can add your numbers. And you can skip the meeting as needed. Thanks, everyone.